much, Moritz, for the kind introduction, and thanks for inviting me. It's always great to be back in Bonn, and I always enjoy being here. This title is kind of addressed towards a numerical audience, which, if I understand it correctly, this is kind of fitting for the audience today. I could give, I guess, the same talk towards a machine learning audience, and then everything would be called Poisson learning instead of Poisson equation. You know, in machine learning, everything has to have the word learning. Jokes aside, what I will present here is essentially you could call it a numerical scheme for a Poisson equation, which happens to be a machine learning algorithm as well. And so then by using, let's say, tools from numerical analysis, we can shed light on that equation and at the same time can hopefully understand the machine learning algorithm better that is behind it. But for today, you don't need to know anything about machine learning to hopefully be able to follow me here. So I will first give a little motivation on why I'm interested in the kind of problems that I will present to you. In particular, the problem will involve a graph, so I will motivate why graphs are interesting. Then I will briefly tell you what is semi-supervised learning. So this is going to be a primer into this subdiscipline of machine learning. And then I will speak about this Poisson equation, which you see here now takes the name Poisson learning, which is a special semi-supervised learning method that is under consideration today. And I will explain you kind of everything that we know about it by now. Okay, so let's get started. Why am I interested in graphs? Well, first of all, because graphs are a very versatile tool to model all sorts of different data. Okay, so starting maybe with this picture or this picture of a cat, you can use graphs in order to describe triangulations of surfaces, right? You can see that such a triangulation consists of vertices which are connected, and then, of course, the structure is a bit specific if you have a triangulation of your surface, but in general, you could use graphs, maybe like this, random graphs, to describe surfaces very well, and then you could try to make some sort of computations on these discretized surfaces. Right? This would be the numerical analysis interpretation of graphs. But then they also appear in other scenarios. For instance, in machine learning, you're often confronted with big data sets, and you want to know the label or the labels of elements of that data set. So if we zoom in here a little bit, here every vertex of that graph is a little image showing a handwritten digit ranging from 0 to 9. So you have a lot of images like that, and you would like to know which digits are actually shown on these images. And so you could start by saying that, okay, maybe I know that this image here is a 4, and this one is a 0, and this one is a 1 or so, and then you try to propagate this information along the graph structure, and you hopefully infer labels of all of these unlabeled data points. And this is kind of the situation that I would like you to keep in mind for the rest of the talk. And from a numerical analysis point of view, what we're doing here is really we're solving a boundary value problem, right, on a discretized domain. We prescribe some boundary datum here, and then we propagate this information inside the discretized domain. Yeah. You can also use graphs for digital twins. So, for instance, to model a digital twin of a brain, where here vertices of the graph correspond to different compartments of the brain, and you have an edge between two vertices whenever these compartments can communicate by means of some electric signals. Or you can use graphs to describe, let's say, highway networks or oil networks or whatever, all sorts of networks. And also here you're typically interested in how does information spread across the network. Now there are two different kinds of graphs. There are so-called metric graphs. So this would be a good example for a metric graph. Because when you look at this highway network, you don't just care about what is the traffic situation in Nuremberg or what is the traffic situation in Bonn, but you want to know what is happening on the edges. How is the traffic between Munich and Nuremberg or between Bonn and Cologne, right? So here on these metric graphs, you often solve some sort of PDE or ODE on the edges, and then you couple these PDEs and ODEs on the vertices, okay? This is the so-called metric graph setting. I'm not going to speak about this today, okay? This is the disclaimer. I will speak about basically all of that here, where we are interested in the vertices much more than in the connections between the vertices, right? We want to say in the case of the brain, if I stimulate that region of the brain, how does it affect that one down here? We don't care how the information travels, but we just want to see the immediate effect, and the same holds true for this labeling scenario. And such kind of graphs are often called geometric graphs for no apparent reason, but they are not to be confused with these kind of graphs. Needless to say, there are a lot of similarities and techniques that you can use for both situations, but yeah, I will mostly speak about the geometric graph set. Okay, so this is kind of the definition that I would like to use. I'm working with finite and weighted graphs. So a weighted graph is just a tuple of a set of vertices, omega n, which is a finite set containing n elements. And then you have this weight function, little omega n, which I will call wn, which assigns weights to pairs of vertices. Okay? Usually these weights are non-negative, and usually this weight function is symmetric. And you can imagine that a pair of vertices gets a large weight whenever they are very similar to each other, and they might get a small weight whenever they are dissimilar to each other. And you can also define the set of edges, which is just the set of pairs of vertices where the weight function is positive. Okay? If the weight is 0, I don't draw an edge, otherwise I draw an edge. And yeah, the situation can be looked at here. Here I didn't draw all the edges which have a 0 weight, but if there is an edge, I put the weight that it has on top of the edge. Okay, so these are weighted graphs. Let me say already here that a weighted graph is a special case of a finite difference discretization, right? Where in a finite difference discretization you have these vertices in a regular grid essentially, and the edges are usually between the bottom neighbors and right and left neighbors, and the weights would be something like 1 over the distance, 1 over the grid size or so, right? Okay, so this is also a very convenient fact because graphs really generalize finite difference discretizations for PDEs. Right.
So what is this omega? This omega without?
Yeah, very good question. So this omega without an index should be thought of as a superset of the set of vertices.
Right.
So think of omega as being a domain in Euclidean space, and omega n is just a bunch of points in that domain. Yeah. All right. So yeah, now let's get to the learning part. So what do we want to do in graph-based learning? So if we have a data set which is represented as a graph, as I showed early on, then there are two kinds of situations. Either you have no information about the labels of the data whatsoever, or you have a little bit of information. This is called the semi-supervised case. The first one is called the unsupervised case. So in the unsupervised case, the only thing that you can do is try to subdivide or partition the data into a certain number of groups. For instance, here I can choose the number of groups to be equal to 2, and I try to obtain a partition like this. Okay? How I'm going to do this is not going to be relevant for today. Of course, I can tell you later, but I'm not going to speak about unsupervised learning today. Instead, I will speak about the semi-supervised case, where you have a few labels which indicate, which indicate some sort of information, and now you want to propagate or extend these labels to the rest of the graph. And of course the result can look kind of different from the unsupervised result, right? Because you now utilized the labels that you have. Okay, another question is obviously how do you go from here to here? Is there a good way of propagating these labels? And I mean there's always a naive way. For instance, you could take any vertex, let's say this one, and then say, let's assign to it the label of the closest point. Right? And then it depends on your notion of what it means to be close. You could travel along the graph and count the number of edges, right? Or you could just look at the Euclidean distance. So there are a bunch of naive classifiers which in 2D always seem to do a good job, but if you really apply them to real data, they never work well. So you have to put some more effort into designing such good models, and these good models, they usually involve some sort of partial differential equation or a discretization thereof.
Would you call that a Voronoi cell also in this context?
Yeah, you can speak about discrete Voronoi cells of the labeled vertices, for instance, yeah, and then you can make the assignment based on that. Yeah, you can do that. It's not the best thing, but it can be done, yeah. And let me also say that this is actually quite costly, because if you're somewhere in the middle of the graph, you have to compute the graph distance to all of the labeled vertices, which is a difficult problem. You need to run the Dijkstra algorithm 4 times in this case, then compare the results and evaluate. So it's not really the cheapest approach. Yeah. Before talking about a specific method, let me tell you what are the challenges in general with graph-based learning. So some of the problems in graph-based learning are actually non-convex. For instance, the partitioning problem is some sort of Cheeger cut problem, which is inherently non-convex. So there you're interested in convex relaxations and guarantees for how close these relaxations are to their non-convex counterpart. I'm not going to talk about this today, but this is pretty standard, let's say. Then there are some questions about labeling guarantees. So can you make sure that the labels that you obtain from this method have something to do with the ground truth labels? But what are the ground truth labels? We would need some sort of model for that. Right? But if you have a model for how the labels are distributed, you could ask that question, and some people do that. Then there's a question on robustness and regularity. So if you take your graph and you remove one edge, or you add one edge, or you remove a data point, or you add one data point, or you shift the data point around, how does this affect the outcome of the method? This is a classical robustness question, and it can be answered for a lot of these models. I'm also not going to talk about this today. What I am going to talk about is the question of large data and continuum limits. That means I want to understand what do these discrete algorithms do when I increase the number of data points, send them to infinity. And this is a reasonable question to ask, because in real life applications you don't just have 25 data points or 70, but you usually have 100,000 or so, right? So you have a really dense sampling of your space. And some of the algorithms work with a lot of data, some don't, as we will see. So it might make sense to understand from a theoretical point of view whether these algorithms have a good limit in the large data regime or not. So this is what I would like to talk about today. Let's now focus on this semi-supervised learning scenario. Just to remind you, what is the situation here? We have our data set. First of all, it doesn't need to have a graph structure in the beginning. You can impose it later on. And we have some labels G, which map from a subset of the set of vertices to, let's say, the reals. So this label function would take the blue value here and the red value here. And now you want to extend these labels. So you want to find a somewhat smooth function, whatever that means, which maps from the graph to R, such that U equals G on the labeled subset. Okay? Why do I say smooth? Well, because a simple solution of this extension problem would be to set every vertex which is white equal to 0, or set it equal to the blue value or the red value. This would of course satisfy this side constraint, but it's not a reasonable solution. So we have to come up with some notion of smoothness or regularity on the graph, which allows us to hopefully extend these labels in a more or less smooth fashion.
So can I just interrupt you?
Yes, please.
You're saying it's not a reasonable solution, but why not? I mean, what is the additional knowledge we have?
Yeah, exactly. There's an additional knowledge or an additional hypothesis, which is called the semi-supervised learning hypothesis or something like that, which says that similar points should have similar labels. If this is something that we can agree on, you should probably introduce a notion of similarity for all the data points and then try to enforce this hypothesis, right?
So the assumption is that, well, the mapping is smooth, so we...
Yeah, exactly. Yeah, but I mean, of course, there's no classical smoothness here because we just have a function on a discrete set. But yeah, it's really what I said, so similar points should get similar labels, so you want to penalize the deviation of the labels for similar points. And we will see in a second how this can be done. Right. So, as I said, to solve that problem, we need some sort of extra notion of similarity. So, unless your data is already given as a graph, you construct a weighted graph, which you can always do because you can always pick a weight function here that is okay. Here now it should probably map from omega to omega. It doesn't really matter. So you can always pick a weight function which assigns weights based on the similarity of your vertices, and then you will get a weighted graph for free, and then you can hopefully solve this extension problem using some sort of graph PDE or a variational problem on the graph. Alright, so this was kind of the introduction. Now I would like to introduce to you two different approaches how to tackle this problem. One which is very standard but has a big problem, and the other one which is a bit less standard but works much better. Okay. So this is really just again the picture that I already showed. You propagate these labels and you get something like that. So a key tool for basically every graph-based learning method, be it an unsupervised or a supervised learning method, is the so-called graph Laplacian. So what is the graph Laplacian? It is a linear operator that maps a function which is defined on the graph to a function defined on the graph in the following way. So you take some function un, which is defined on the graph, maps to r, and you compute this quantity here. Okay? So you sum up, so at a point x, you check how much does u deviate in this neighboring values. So you look at all the neighboring values of y, all the neighbors y of x, encoded through this weight function, and you sum up these differences here. Okay? And obviously, if the weight function is chosen in a clever way, then you will only do this sum over points y which are similar to x in some way. Okay, so why is this called the graph Laplacian? Shouldn't the Laplacian have some sort of different second-order difference quotient, right? This looks like a first-order difference quotient. But no, this is really a good notion of Laplacian, and there are multiple reasons. So the first one is that this minus this operator is a semi-positive definite operator, symmetric positive semi-definite operator on the space of graph functions with respect to a certain inner product. So that's already a good property, which is also enjoyed by the standard Laplacian. Second, if a function has zero Laplacian at a point x, that means that un of x equals the mean value of its neighboring values. So we have a mean value property, which is also satisfied for the standard Laplacian. There's another reason why this should be the Laplacian, namely, if you say that un is actually a smooth function that I restrict to the graph, so I have a smooth function on Rd, which I just evaluate on the graph, you plug in the Taylor expansion of u here, and you will see some cancellation of the first order terms if the weight function is isotropic, and you will get the Laplacian plus some error terms. Okay, so there are a bunch of reasons why this is good, or why this should be called the Laplacian. Alright, so now what are the challenges? So there is this very straightforward approach based on the graph Laplacian, which is the following. It's called graph harmonic extensions. This is a paper from the early 2000s. It has thousands of citations now, and what they propose to do is the following. Fix un equals to g on your label set, and then say that on the complement, so on all the unlabeled vertices, the function should be graph harmonic. Okay? This is maybe a good choice. So for every point, the label should be equal to the mean value of its neighboring labels, so maybe this is a reasonable approach. So let's do this for this graph here with two labeled points, the blue and the yellow one, and a few unlabeled points, the gray ones. Now here I plot the solution, so I rotate the plot a little bit, right? So you see the solution. Here it takes values close to 1, close to -1 here, and then there's some intermediate values. Now let's use this for classification by cutting at the 0 level, and we get a reasonable clustering. We say everything which is on the right should belong to the yellow class, and everything which is on the left should belong to the blue class, which kind of fits to your labels, right? Great, so now let's increase the number of data points. So now I have a lot of data points, you don't even see them anymore. Just at the boundary you can see some round shapes. This is the solution that I get from my Laplace learning approach. And now I cut it at 0 and I get this meaningless classification, right? So it doesn't work at all. Does anyone have an idea why this doesn't work if there are a lot of data points? Any idea? So if you think of a PDE, let's think this is the PDE Laplacian u equals 0 on omega, complement subset O, u equals to g on O. So for the Laplace equation to have a solution which is not the constant solution, you need that the Hausdorff measure of that set O is d minus 1, right? You need O to be the boundary of a set, or you need it to be a hypersurface, because then you have then a Sobolev function has a trace on that hypersurface, and you can prescribe a value here. If I just have a few points, the only solution to the Laplace equation is the constant solution, which almost everywhere agrees with the boundary values then, because the boundary values have zero Hausdorff measure, or zero Lebesgue measure even. So this is not very surprising that we're converging to a solution which is essentially constant outside of a set with Lebesgue measure 0 and Hausdorff measure 0. So this cannot work. Still, in applications, everyone uses that method. Sometimes it works better, sometimes it works worse. But here we see that it's not a good method in the large data regime, so it needs to be modified. And you can prove theoretically that this is what's happening. So you can prove that Laplace learning always converges to a constant solution, very useless, unless the number of labeled data points grows sufficiently fast. Here it doesn't grow at all, right? I just have 2 labeled data points. But actually, the number of labeled data points would have to grow at the same rate as the number of total data points. So that means you basically have to label every second data point or something like that, which is completely ridiculous in applications. So this cannot be used in the large data regime. Now there's another method which was proposed, 20 years later, and which works much, much better. And the reason is, why does it work better? And I'm trying to answer this question through mathematical analysis. So this method is called Poisson learning, and here the idea is to replace the boundary value problem that we have with fixed boundary conditions by a source term. So we put a source term on the right hand side of the Laplace equation, so we get a Poisson equation, and we encode in some way the labels G into the coefficients of that source term. Okay? So what is that source term? It's a sum of Dirac deltas that are located at the labeled data points. So On is a set of labeled data points. So you put a Dirac delta wherever you have a labeled point, and you multiply with some number ax that depends on the label value. And you get a Poisson equation. Now if you do that, you get this beautiful solution here, which looks much more reasonable than the one of Laplace learning, and you threshold and you get a nice classification. Okay? So this works very well. You can also test this on real data sets, not just this toy image here. It works very well. And the reason is that this Poisson learning problem has a good continuum limit. So there's a PDE which is satisfied in the limit. And you can derive the PDE and you can characterize convergence to that PDE. All right, so let's do that.
A quick question.
Yes, please.
What does it mean for you to have a nice classification, like in this example, just to that it's cut through in this axis, right?
Exactly. So my labels were like this, right? So the only reasonable, there are multiple reasonable classifications, right? Maybe a yin-yang shape would also be okay, right? In principle, this might also be a reasonable classification. Maybe I should have added a few more points here and there, which wouldn't have changed anything actually. But the classification that I want to see is really the one which cuts here in the middle. Okay?
Okay.
Yeah. But in principle, you're right. Anything is a reasonable classification. But Laplace learning doesn't give it to you because it always converges to a constant solution.
Yeah, okay. I see. And how are the weights chosen in this example?
Just based on the distance of the
Okay, I see.
Yeah. And it doesn't make actually a big difference how you choose your weights. You will always observe the same issue.
But so,
yeah,
intuitively, instead of saying, okay, I want this pointwise, you're saying, okay, on average, I want the data to be right. The Laplace UN is the average. It should be, my data should be enforced on average. Or is that?
Yeah, but how do you enforce that on average? If you just have 2 or 5 labels, let's say, and what do you want to do?
Yeah, okay.
Let's discuss this later and find a new semi-supervised learning method. Okay, there are actually, what some people do is they penalize the deviation from the data, so they say Laplacian U equals, and then you have a source term which is U minus G, essentially, on the set of labeled vertices. So by this you enforce kind of the U is equal to G on the set of labeled vertices, but then again, since this is a very small set in general, it has much smaller dimension than the ambient space, this also doesn't work. Okay, so let me now tell you about these continuum limits. How do we do that? Because I think this is of general interest, because you can use techniques like that basically for any kind of discretization of a PDE that you might have with a graph. Yes, there's a question here.
Yeah, can you go back to the, so like on the right hand side, this image, the partitioning into yellow and purple, I guess, is it just based on the value, like there's a certain threshold?
Exactly, a threshold at 0, yeah.
And so what I see is that like the function like has like quite steep incline close to the data point.
Yes, yeah.
Like, does this change if the points were further apart? Would that be like a bit softer?
Not really, because it's a solution of a Poisson equation, so it will actually always grow like the fundamental solution of the Laplace equation, even if they are far away from each other. Yeah, but this is not it's not harmful for us. What it is harmful is to have these infinitely steep spikes here, essentially, right? Okay. Yeah. So what do we want to do? Yeah. Essentially, we have our graph equation. We want to prove that if the number of points goes to infinity, we converge to some solution of a PDE. Essentially, that's what I would like to do now. And in particular, this is kind of the key feature of my research. I always want to make things quantitative, so I want to prove rates of convergence as well, in terms of the number of graph points, for instance. So how does one do that? I already spoke about the weights. Now here's a specific way to choose the weights. There are essentially two ways. This is one of them. You fix the so-called bandwidth or communication radius or whatever, epsilon, and you fix a function eta, which is non-decreasing. And non-increasing, sorry, and then you define the weights to be like this. So this means that whenever the distance between two data points is roughly smaller than epsilon, the weight is going to be large. Whenever the distance is bigger than epsilon, the weight is going to be small. So here's an assumption on what this kernel eta should satisfy. And typically people either choose this one with a hard threshold or they choose some exponentially decaying thing. Then there's a second quantity, which is also equally important, namely it's the resolution of the graph. So in finite elements, you would say it's the length of your triangles or something like that. It's just the fineness of the discretization. And to define it, I have this Hausdorff distance here, which is defined like that. It's just the maximal distance between a set and another set. Okay? And I define this graph resolution delta to be the Hausdorff distance between my set of graph points and some limiting domain, which I would like to approximate. And I also take the maximum of the set of labeled points with some set of limiting labeled points. If you don't want to change the labels, you can set ON equals to O, and this term is just 0, it doesn't contribute. So this is really, if you wish, the grid resolution of your graph. And now those two parameters, they have to interact in a certain way to get convergence. So first of all, the resolution has to be smaller than a constant times the bandwidth, otherwise your graph is disconnected. But if the resolution over the bandwidth is smaller than a certain dimensional constant, your graph is connected, which is actually more or less a necessary criterion for having a good continuum limit, or having a continuum limit in the first place. Second observation, this resolution delta n scales like this, essentially up to log factors like 1 over n to the 1 over the dimension, if the graph is an IID sample from some probability measure supported on RD. For those of you who don't like probability, just think of a grid graph, so like a finite difference grid, then you will have 1 over n to the 1 over d. The logarithm will not be there, okay? This is just by Pythagoras' theorem. And the logarithm just accounts for the fact that for a random sample there might be some holes. With small probability there's some hole which is not filled with samples. So this is the scaling of the resolution. And now everything in this continuum limit business will be based on these two quantities, delta and epsilon. So the resolution of your graph and the bandwidth that you choose. This is not something that you can choose as a practitioner, because the graph is given to you, the data is given to you. You cannot say, I want to have 20,000 more data points. In general, this is not possible. But you can choose the bandwidth. So this is just a computational parameter. The bigger it is, the harder it is to solve your problem, because everything will be super non-sparse. The smaller it is, the easier it is to solve the problem. But it cannot be too small, otherwise this condition is violated. Right. So now let's finally look at Poisson learning. this is the equation, I already showed it to you, so minus the Laplacian of u should be equal to some right-hand side, which has Dirac deltas located at the labeled vertices, and then here you have the labels minus the mean of all labels. This is just for the right-hand side to sum up to 0, not very important. And then to have uniqueness up to translation, you also fix essentially the mean value of your solution u. So this should be a bold u, I'm sorry. So you fix the mean value to be, let's say, 0. Otherwise, you can always shift your solution un up or down, and the Laplacian wouldn't notice that. So this is the graph equation. Now this is the limiting PDE. So here you have a Laplace operator, which involves some diffusion coefficient rho that I will get to in a second. And then here you have the same right-hand side, essentially, Dirac deltas at the labeled points, subject to some Neumann boundary conditions and to some normalization of the mean value. Okay, this turns out to be the limiting problem. And now let me remark that since the right-hand side is a measure, the solution of that problem is not W12 or so, it's just in W11 in general. Or you can prove W1p for a tiny p, but essentially it's in W11. It's a distributional solution, not a weak one. So what are the ingredients? So the labels, for now I fix them to be binary, this is not important at all, but let's just imagine that they are either -1 or 1. G is the mean value of all the labels. It is 0 if you have equally many points in one class as in the other one. Then the graph consists of IID samples whose law is precisely that function rho, which appears here as a diffusion coefficient. I assume that this law has a density with respect to the Lebesgue measure. So this is really a function. And then the set of labels is a finite set. And the set of labels on the graphs is the projection of that set onto the graph. And what is the final labeling decision once you solve that PDE? You take the sign of your function. Whenever the function is positive, you say this is class 1. Whenever it's negative, you say this is class -1. This is what I did in the numerical examples that I showed you earlier on. Right, and now the task is, I want to show that this is indeed the continuum limit of the left-hand side. And I want to do this quantitatively. So I want to say something about the solutions un and u. How do they relate to each other in terms of the difference of the norm of their difference? Right. So maybe just some remarks here. This Poisson learning method was proposed like 6 years ago. Very good results, but no theoretical analysis. There is no variational interpretation of this problem because of the singularity of the right-hand side. So the solution is not a minimizer of any energy. There is no energy here. So you have to use PDE techniques. No variational techniques are possible. And we want to prove convergence rates. So this is the statement. I'm dropping a few assumptions here. Epsilon was this bandwidth parameter, and it can go to 0. It should go to 0, otherwise you don't get a limit. And it should go to 0 not faster than this, which is the cubic root of the resolution of your graph. Right? Remember, the resolution was log n over n to the 1 over d, so this is the cubic root of that thing. So epsilon shouldn't go to 0 too fast. It should go to 0 slower than this expression. Then, with high probability, that means exponentially high probability, it holds that the solution of the graph problem converges to the solution of the continuum problem in the graph L1 norm, and this is the convergence rate. So it depends on the bandwidth, which is a quantity that goes to 0 to some exponent here. And let me remark that u is a W11 function. So in particular, we can think it's measurable. It has a measurable representative, so we can evaluate it in these IID points. So this quantity is actually a well-defined expression. So we can evaluate u at random points, not at deterministic points, but at random points. We can do it because the probability of a random point to hit a non-Lebesgue point of u is essentially 0. Okay? So this is why this is well-defined, and the convergence rate is here. Now you can choose this value of epsilon if you want to, or a little bit bigger, and you will get some expression which only depends on the number of points n. Okay, it will be essentially 1 over n to the 1 over 3d. This will be more or less the convergence rate. So it is pretty bad if the dimension is high, but that's how it is. This is for now the best result that is available. And if the density of your sampling is constant, so if you sample uniform points, then you can improve the rate a little bit. So then you have 2 over d plus 4, which is actually better than this rate if the dimension is bigger than 3, I believe. Question? Yes.
Yeah, did you think about boldface usage and doing the measure, the error estimate by extending boldface use?
Yes, you can do that. You get exactly the same rates actually. So you can do a piecewise constant extension on the Voronoi cells of every graph point essentially. So you get a piecewise constant function. You can compare this to U, and you get essentially the same error estimate. Yeah, and this is it's even used in the proof in some step. So yeah. If you have a graph function, you can extend it to have a function defined on the continuum, and if you have a continuum function, you can restrict to the graph because the graph is random, and you get the same convergence rates for both expressions. Yeah. I will get to that extension when we speak about the proof in a few minutes. So on a high level, how does one prove a result like this? So since there is no variational interpretation of the PDE, one has to work a little bit. So the first thing that we do is we take the right-hand side on the continuum, which is this measure, and we modify it with a function phi. So we replace the Dirac measure just by some functions phi x, which have their support in a ball around x. Okay, so this is going to be a L1 function, even a bounded function. So we replace the ugly data by a nice one in the continuum, and we prove some error estimates in terms of R. We do the same thing for the graph. So we have this right-hand side on the graph. Now we modify it by using the graph heat equation. Running the graph heat equation for k steps, and then we get some quantitative estimates how the solutions will change in terms of the number of steps that we run the heat equation and epsilon, which is our bandwidth. And now you put yourself into the situation where the data is nice because we modified it, so now the data is a bounded function, so we have a variational interpretation. And so for bounded right-hand sides, we use variational methods and some strong convexity to prove a continuum limit. So these are the 3 high-level steps that we have to take. Now there's not so much time left, so I'm trying to think which one I would like to present to you. Yeah, let's see. And yeah, how do we get a rate then in the end? Well, we have a bunch of constants here. We have R, which is this modification radius. We have K, which is the number of discrete heat equation steps. We have epsilon, and we have delta. And so when we patch everything together, we get a huge expression. And now we have to choose constants in such a way, these constants in such a way that we get a convergence rate. So this, just very briefly, this shows how you do the modification. So if you take your Laplace equation, you modify the right-hand side, you can prove an L1 estimate. So the difference of the solutions in L1 will be essentially proportional to the modification radius squared. Well, this is not exactly true, it's 1 plus beta, for beta smaller than 1. But if the density is constant, we can actually get R squared. So yeah, this can be done. How do you prove something like that? So maybe I'll explain this a little bit. How do we prove this? Because we have 2 PDEs, one of which only has a distributional solution, not a weak one. So we prove a new stability result for this Poisson equation with a measure right-hand side. And the measure is later going to be the difference of those 2 measures here. And this stability result, we couldn't find it anywhere, so maybe it's new. Is that you get LP stability for small values of P. So the LP norm of U is bounded by this quantity, which is a dual norm on the space of measures. So note that the space of Hölder functions is embedded in the space of continuous functions, obviously. So this is smaller than the total variation norm of the measure mu, because we take a smaller set of test functions. So it's a weaker norm than the total variation norm, and using this new norm here, we can then prove the previous estimate. Now, how do we do the same thing on the discrete level? We define a new Laplacian, which is not our Laplacian that I showed to you, but we normalize it with something that is called the degree. And then you get something which is called the random walk graph Laplacian. This is really just for convenience. Think of L hat just being L, okay, for simplicity. And now you can define the heat equation. What is the heat equation? Since everything is discrete, we say that we start at a Dirac delta, and then we have some explicit Euler method here with time step epsilon n squared, which is the bandwidth, and we use here this graph Laplacian transpose. So this defines what we call the graph heat equation, and the solution of that graph heat equation, we call it the heat kernel, as in the continuum setting. And once we have a heat kernel, hk, we can convolve with that heat kernel. We can convolve a function u with that heat kernel using this formula. And now we have a beautiful result which says that the convolution commutes with the Laplacian, okay? Like in the continuum. You can, if you have a convolution integral, you put a differential operator in front, you can pull it inside, right? And here we have the same thing. Now this means that solving the Laplace equation with a convolved right-hand side is the same thing as convolving the solution of the original Laplace equation, okay? So that's great, because now if we have our two Laplace equations, one with a convolved right-hand side, one with the original one, we know that the difference of the solutions is just the difference of u minus its convolution. So we just have to estimate how well does the convolution operator approximate the identity. This is the formula. You can take norms. You use that the heat kernel has norm 1, and then you have k steps of the heat equation, so you get a k. The 1 over m cancels with the degree. You get k epsilon squared times the norm of these weights. So k epsilon squared corresponds to this modification radius of r that we had previously. Okay? So k epsilon, so actually the square root of k times epsilon is the average distance that a random walker travels in k steps on that graph. So this can be interpreted. Okay? So this was really the key ingredient, I would say, to figure all of this out. And yeah, so now we put ourselves into the position where all the right-hand sides are nice and bounded because we convolved them. Now, how the heck do we prove a continuum limit for such a problem? Yeah, so this is the answer, okay? The solution of this equation minus the solution of that equation, they satisfy this beautiful estimate. Okay, obviously you don't have to look at the terms. But there are a bunch of terms, namely the red ones, which will all blow up as we let the modified right-hand side converge to the original right-hand side. Okay? So the oscillations will blow up, the LQ norms for q bigger than 1 will blow up, obviously the L infinity norms will blow up, everything will blow up apart from the L1 norm, because the convolution preserves the L1 norm. Right? So all of that blows up. So we have to counteract that by choosing the parameters epsilon and delta and lambda that you don't know of in such a way that they cancel the blow-up of the red constants, and this will give us a rate in the end. Okay, I'm not going to do this obviously, but I want to tell you how do we prove this inequality. So how do we get a continuum limit here? And there's a very nice variational technique which goes from the discrete graph equation to an intermediate non-local equation, and from there to a local equation, essentially using Taylor expansion. So how does this work? We can define a discrete Dirichlet energy, which is just the energy that corresponds to the graph Laplacian. So it's basically un of x minus un of y squared times the kernel. And now, if you take a function un and you extend it to the continuum, as you said earlier on, so just piecewise constant extension, you can actually upper bound a certain non-local Dirichlet energy of that extension in terms of the discrete Dirichlet energy of the function un itself. And now we can do something else. Take a function on the continuum u and modify it with a cleverly chosen modifier lambda. Then we can actually control its standard Dirichlet energy in terms of the non-local Dirichlet energy. Okay? And now we put this all together and say, let's take our graph solution, let's extend it, and then let's modify the result. Okay, so we have solution just on points. We put a piecewise constant extension, which is a step function, and then we modify it. And now the result of that has a Dirichlet energy, which is controlled by the discrete Dirichlet energy of the solution UN itself, which is a so UN is a minimizer of the Dirichlet energy, so we have some good properties. And by this computation, or by this arguing, this funny function is actually a competitor for the variational problem that defines U. So we can use it to have energy estimates between U and this modification. And then you have to just undo the modification and the extension with some other error estimates, and you get the formula that I showed. So yeah, this was the proof strategy. Now let's get to the end. What did we discuss today? So Poisson learning is essentially just a finite difference approximation of the Poisson equation, and it has a continuum limit, namely this Poisson equation that I showed you. And we can even prove convergence rates in LP for small values of P. Okay, there is this restriction that the length scale epsilon n has to behave like this, which is not so great in applications, but it's the best that we could do for now. And the proof is essentially based on this 3-scale proof technique. So there's the discrete problem, which is 1 scale, where we modify with the discrete heat equation. And there's the continuum problem, where we just do some standard modification. And then there's the continuum limit for the intermediate problem. And then we patch it all together. So future work will be sharpness of these rates. So we already know that the exponent 1/3 is not sharp, but it's also not 1. So from our numerical examples, the rate is somewhere between delta to the 1/3 and delta to the 1, but it's definitely not a linear rate. But yeah, it's pretty hard to pin down where the non-sharpness actually arises. So what my personal conjecture is that there's a 2/3, because in this whole business, you always, at the end, you take a square root, which you shouldn't be taking, but you have to do it. So in the end, I think that the rate actually is delta to the 2/3, but let's see. And then there's one last thing that we would like to do, namely I showed you this new stability result, which we proved for the Poisson equation with the measured data. If we could prove the same thing for the graph Poisson equation, that would be great. But unfortunately, there's no Gilbert-Schrödinger book for graphs, essentially. That's really the problem. So on a graph, you can do L2 theory nicely. So you can do Evans on graphs, let's say, but you cannot do Gilbert-Schrödinger on graphs. That's really the biggest problem. Otherwise, we would have much easier proofs and probably also better rates. Okay, so thank you very much for the attention. This is the preprint. It's 120 pages, so I don't recommend you to read it. If you want to know something about it, better ask me. That's why it's been under review since 2 years. Cool. Thanks, and I'll be happy to answer questions.